the workbook this week, or this chunk, will walk you through the theory of generalized linear models. And we'll have kind of the conceptual lecture for generalized linear models on Monday. So for this practical, all I'd really like to do is show you the stuff before we get to the generalized linear model. So that'll just be the kind of conceptualization and kind of logic behind how regression represents what I'm calling a distributional model. So the way that I would encourage that or get you to follow along locally is to read in the waiting times that are in the course the course data repository. And so these times are just a set of observations where waiting is the number of minutes between when you put in an order and when you get your pint or drink. The pub here is the actual pub where the order is made. And then this pub number is just like a index that represents the pub on the left. So it's if you want a numerical version of the character vector that describes the pub to the left. Okay, so in reality, we only really have the information about the pub and the information about your waiting time. Okay, and that's this data set. So if I asked you, what is the average waiting time in each pub, we could be using a group by. If I have times and I wanted to get the average wait time per pub, then I would need to be summarizing all of the pubs. So I need to group it by pub and then get the mean, is it time or waiting? I need to get the mean waiting for every pub. Does everybody see that? Very simple, group by and summarize. I need to know the average within a group. So I make sure that my group by has the group I need to summarize on the furthest right. And then I pass that to a summarize, which then takes that furthest right group and constructs a summary of the rows that fall into that group. So what this is doing is it's splitting the data frame by pub, and then it's getting us the mean of the waiting variable. And I can do more than just mean. I can also get the standard deviation. I could get whatever I needed to. Okay? So this is just a very simple summarize that gives you the pub average waiting time. So if I asked you, what's your best guess for how long you're going to wait if you go to the galley? What is the best guess for how long you're going to wait for your beer at the Gala Malfrey? If you want to put it in the chat or voice on, that's fine. What would be the best guess for the number of minutes you'd wait for your beer at the galley? 14 plus or minus 1.06. Reasonable. I would even say just 14 or 1.4, right? Yep, perfect. So that's your best guess. And you all are kind of implicitly suggesting that that's the best guess, maybe because I've shown it to you. Why is that guess maybe better than that guess? Well, we're used to thinking about the mean rather than the median. But in this case, we might have extra long waiting times that are biasing our understanding of what guess we should make about our waiting time. But the mean's a relatively good idea. We won't really talk about robust estimation, which focuses on medians, like linear regression based on medians rather than linear regression based on means. But it's just good to know that again, as we were talking before, there's a bunch of different ways to construct your guess. So 1.4 is the mean, but 0.8 is the median. So our mean might actually be a little bit tricky to, and you see how in the Berkeley, your median is longer, and in the Galley, your median is smaller. So it can be interesting when it comes to skewed things anyway. How you construct your guess can change your guess quite significantly. But just focusing on the mean. Okay, so we get this mean for waiting time. Now, in the times data, if I wanted to use a linear regression to do something similar, I could fit the following model. I want to predict waiting time based on what pub you're in. Has anybody seen this kind of linear model before? I hope so, because it was on your Spatial Modeling 2 final. This kind of model is called a fixed effect model. And it's called that because we're just sticking in a dummy variable for each pub. So you'll notice something here. When I fit this linear regression and I use this group by, the intercept corresponds to the average wait time in the Berkeley. The effect of being in the Gallimaufry, this pub Gallimaufry coefficient, is equal to the intercept was equal to the Gallimaufry 1.04 or 1.4 minus the Berkeley. So like is typical as you've learned about linear regression coefficients, it is the effect of moving from the default into a category, into that category. So here, if our intercept is 4.7, then the effect of the Gallimaufry variable is the change in waiting time between the Berkeley and the Gallimaufry. So this is sometimes called a contrast. If I have a categorical variable, I need to set one of the categories as my reference category, and then all the other categories are estimated in reference to that. So this effect is going to be the total waiting time at the Galley is going to be the intercept plus the effect for the Gallimaufry. Because if I wanted to actually write out how to predict my waiting time at the Gallimaufry, I would do 4.7 as the intercept plus negative 3.3 times, if I'm in the Gallimaufry, I'm going to put true. And then if I am in the milk thistle, I still need the 1.56, and I would need false. So the intercept is there for every observation. And then when I'm in the Gallimaufry, I turn on that effect by putting true. And since if I'm in the Gallimaufry, I'm not in the milk thistle, I have to put false for being in the milk thistle. And that results in the mean waiting time for the Gallimaufry. Does everybody see how that works? If you just naively put in a categorical variable into a linear model in R, it converts it into this kind of contrast coding. Likewise, we could see, for example, sorry, I'm in Python mode. If we were in the milk thistle, we'd have this example. So we still have the intercept. We have the Gallimaufry effect, but because we're not in the Gallimaufry in this example now, we put false there. It's 0 now. We're not in the Galley. We're in the milk thistle. If I add that together, then I get 6.265, which after rounding is the same as the mean you see up there. And obviously, if both of these are false, I have 4.7, which is 4.7. So does everybody see how these categorical variables are reconstructing the means in each of the groups? The other way you can verify that this works for yourself is using the predict function in R. So predict takes a model and then gives you back the predictions for your group. We'll be using this function a lot. So how it works, let's say we have a model like before. Weighting is a function of being in your pub, and then your data is times. Okay, that's our model. If I predict on the model, that gives me the values for every row of the data. So if I had times, every row is going to have the prediction corresponding to its row number. So predict model just gives you back the predicted Y for every single row of your data frame. This means that you can string this together with the tidy tools you've seen before. If we say times and then mutate predicted weight is equal to predict model, and let's just get the first 5 rows for simplicity. Just to walk over this pipe one more time, I'm taking the original times data, I am mutating it to add a column of the predicted weight that contains the predicted weight times from my model, and then I'm getting the first 6 rows, or 5 rows. If I run this, I get a new column that tells me the predicted weight. And you see that all of the observations in the Berkeley have the same predicted weight. It's just the mean for that time in the Berkeley. So as Tom and James write in the chat, that's the model's prediction, or sorry, not exactly the numbers that they're writing in the chat, but as they wrote conceptually, that's the prediction from the linear model. Is everybody seeing that? If I go with 8, now the predictions for the Berkeley remain the same. Patrick, you may need to library tidyverse. And you may also need to read in the data as times. So if you see here, again, the predictions for each of the groups is equal to the mean weight. Okay? Now, the other way that we're going to use predict is by constructing fake data frames. So I might say that I have a scenario where I have 3 observations. 1 in the Berkeley, 1 in the Gallimaufry, and 1 in the milk thistle. So this is just a data frame where I've made a new column that contains the values I want to predict for. Does everybody see that? When you use the data frame function, if I put column, it works basically by having a column name that is then equal to some set of values. So like if I did sequence from 1 to 10, I would have a data frame where one column is column name and it has values 1 to 10. And then I might do other column is equal to, let's say, 10 to 20. Oh, whoops, 10 to 19. So you can just stack on the various columns that you want to build, and the data frame constructor will turn them into columns for you. So all I'm doing when I say I have a scenario where I'm going to store it in the data frame, it's got one column called pub with 3 values, which are the 3 pubs we're going to wait in. Okay, does everybody see how I constructed that? This is the only other way that we'll be working with the predict function. So if I use predict on the model, I get back predictions for every row of the data frame. If I want to predict at a specific value or a specific collection of values, I can build that scenario and use it as the second argument to predict. So what this does is gives us the predictions our model will make at the rows that encode our scenarios. Since our model only uses information about pubs, all we have to do is build a data frame with a pub column. If our model contains more than just information about pubs, as you'll see in a second in the workbook, then you'll need to build a scenario which has columns that represent each variable in the model. Okay? So predict can give you back the predictions for the data that you've seen, and it can give you back the data for things you haven't seen. So this is the in-sample prediction in the language we were talking before, and this is the out-of-sample prediction. So to make an out-of-sample prediction, we run something like this. So scenario is just the 3 pubs, and the predictions correspond to each row of the scenario data frame. We'll be using that in the workbook as well. Okay? So, yeah, right. So we've been with a model that has this formula. Waiting time is a function of pub. And we've seen that these, well, the intercept represents the mean waiting time in the first pub. And we've also seen that this effect is something called a contrast that moves us from the first pub to the waiting time in the Galimau-free. And you can think of it kind of like the same as a marginal effect or a beta in a continuous variable, because it's the effect of changing from one pub into the other pub. So this is the effect of the change in waiting time relative to the Berkeley of going to the Galimau-free. Okay. The other way that you can fit that model is using what's called a direct form. So rather than fitting it in a contrast form, we fit it in a direct form. To do that, we don't want to fit an intercept, and we use that -1. So what that does is it says, okay, now I don't want to have any overarching intercept. Instead, I want to fit a model where each group has a separate intercept. Does that make sense to folks? Does everybody see how I got there? If you do -1 at the end of your expression, you'll remove the intercept. You can also do 0 plus, and then you'll remove the intercept. It doesn't really matter either way. Both will be valid when we get to the rest, but let's proceed with 0 plus. So you see now, with this linear model, we get exactly the means for the effects of each pub. So thinking a little bit more conceptually, I guess, if we were trying to construct the prediction about a pub which wasn't in this list, how would you do it? Well, each of the pubs has a really different distribution of waiting times, right? So the Berkeley, has minute waits between about 1 and 6 minutes. The Galimau-free has some half-minute waits, so has 3-minute waits. And the milk thistle seems to have really variable weights, with one time being up to 15 minutes for a drink. In addition, we haven't sampled these bits of information at the same number of times. So we've only gone to the milk thistle 4 times. So we have less information, and that contributes less to our guess about what an overall wait time would be for a pint of pub. We'll deal with this particular problem of how to generalize from information that contains stuff about groups in the next chunk on multi-level models. But right now, we'll just leave it to be said that in this model, there's no explicit prediction for pub. If I say predict our model, and I want to know what the prediction is for, let's say, a new pub, we get error. Factor pub has new level Eldon House. And if I fit for that model, that's a contrast model, my implicit prediction for anything I've never seen before has the exact same wait time as the Berkeley. I could flip that around and make my reference category something else, but I'm still making the same predictions as, relative to pub. So this kind of fixed effect modeling, where we're introducing an individual intercept for every group, is a very common strategy that's used in linear regression, and we'll hit it a lot later. But I just to show you about how we're constructing these expectations of waiting time using the linear version. Hannah asks, can't the intercept be the mean for all groups? In linear regression, you have sort of a concern about something called collinearity. And collinearity happens when an effect or one variable is recoverable as the exact combination of a linear combination of any other set of variables. So if I had an intercept estimate and then differences for all the other groups, I could find weighting of those groups that exactly covers the intercept. Mathematically speaking, that is not well conditioned. And if you do a model that has perfectly collinear effects, you get nonsense results. In fact, sometimes you get infinities or not a number, because it causes the covariance matrix to be ill-conditioned. So in a standard form, just using typical effects, we're forced to do this kind of contrast coding. You don't have the ability to model the mean for all groups and conditional effects for every single group at the same time. So the point here is that all of these coding methods are still just ways to predict things individually group. The other model that we fit would just be a model with a constant. Which would predict the mean waiting time. And we could use those two models in tandem, but we'll see in the next chunk how multi-level models will help us sort of tie these two things together. But my main point is to show you that all a linear regression is doing, especially when we have categorical data, is constructing a guess about the group. So it's exactly the case that if I fit a model with the effect, that is the mean for that group. That's all I really wanted to hammer on this particular encoding until we get to multi-levels at least, and then we'll revisit this. Okay. So what I show in this workbook and what we'll get to a little bit more in the lecture on Monday, is that if I have like times, are equal to, okay, so I'm just focusing on the Gallimaufry here, right? Yeah, so if you have to repeat the statement I made about linear regression, all I want to show you from this particular point is that when you fill linear regression, it's just constructing the guesses about groups of observations. So it's just a fancy way of fitting a lot of means at once. How you read this is, given that in the Berkeley, our wait time prediction is 4.7 minutes. It's just a way to guess about the mean of groups. Okay? So, focusing just on the Gallimaufry, our mean wait time in the Gallimaufry was 1.4, right? Something about that. Okay. Some of these observations are above 1.4, and some of the observations are below 1.4. So I could, in theory, use the resid or the residual. We'll use that one because we're not seeing on the keyboard. We'll use the residual function to get our errors. Has everybody seen the residuals function before? You should have. I believe that it's commonly taught. So what this does is it gives you back the prediction errors for your model. And just like before, I could say, you know, put times, and I could say, error or residual, and then we'd see the residual here. Okay? Now, if I were to say, I don't know, times equals pub, y equals, okay. So if I have the waiting times for the individual pubs, there's a little bit of skew. You can see that, you know, the median line is higher than the IQR or a bit lower depending on the pub. But the point is that each of these things has a mean, right? Or some indicator of the centrality of that group. And then also has a different dispersion. So when a linear model is fit, let's actually focus on the one that was fitting function is 0 plus pub. Okay. We get these standard errors. So we know that these are the means. If you had to guess, what are those standard errors related to? Isabel asks, is 0 the same as pub minus 1? Yep, totally. Well, just so happens that those standard errors, the effects, it is indeed information about the spread of waiting times for each pub. Good job, Noah. So this is, if I were to think about how these waiting times relate, I would say summarize, and we do the mean waiting, and then the SD waiting, right? So these are functionally related to one another. This standard error and this, and I think I put that in the workbook. But the main kind of point here is that the residual standard error is a function of this standard error as well. So if we have resid for our model, and we look at histogram, those residuals, oh, it's not going to like that because it's, I see that it looks kind of normal, right? And what this is doing is it's taking each group and it's mean centering it, and then it's looking at the deviations from the center in each group. Residuals for the model are going to take the difference between our prediction and the observed, and our predictions are just the mean of each group. So we're just piecing together the bits of the regression model now. So altogether, what this means is that our linear regression is actually a distributional model. When I fit a model like weighting function of pub, so let's start with just a constant. So in the constant model, all I'm doing is fitting the mean. So that is, say, times summarize mean weighting ST. This is that. That is that. The mean waiting time is the same as the intercept in the constant model, and the standard error on the regression is the same as the standard deviation there. Okay? Now this gets a little bit more complicated as we introduce, then what is the standard error here? That's the actual, that's functionally related to the standard error of the mean. Is different from the standard error of the data. So I'm not sure if they covered this in your introductory lectures, but the standard error of the mean is our uncertainty about the estimate of the mean. It's functionally related as well to the deviation in the data, but it's not exactly that. Okay? So the point is that the mean and the standard deviation are related to this estimate and our residual standard error, and in part the standard error of the estimate as well. For the grouped model, you'll note that this residual standard error is smaller. So above, we were just talking about this standard error. Now it's smaller. Okay? These are still the group means. What this implies is that the model from, I'd like to switch to the actual rendered work now, just because it's a little bit easier to see. What this implies is that is a special form of a model. Can everybody now see the workbook so we can follow along? What this implies is this special kind of model. If I'm in a given pub, then this model that I fit is going to be suggests that we wait about 4.7 minutes in the Berkeley, about 1.4 minutes in Galley, and about 6.25 minutes in the milk thistle. And it's actually going to imply that you have a bit of a normal distribution where the variance of all those things are the same. The variance of all of those things are going to be our common residual standard deviation, or a residual standard error. So in this next part, what I'm doing is I'm showing you how this conditional expectation can even be used to model binary variables. Okay, so in this first part, all we've been doing is talking about how linear regression gives us effective sort of guesses or summaries for the average waiting time in each pub. In the next part, we're going to try and predict whether or not a friend of ours thinks a long wait, things that a wait in a pub is too long for them, based on the pub they're in, but then also the amount of time. And eventually what you'll see happen is that the predictions that we make based off of these models, it's really easy when all we have to do is summarize a single variable. But now we've got a different intercept and the effect of the length of wait. So it gets a little bit more complicated. Further, we don't have any means to deal with anymore because our outcomes are binary. So the way that we construct these conditional expectations, in the first part, it was all about just looking at the mean within groups. In the second part, it's going to get a little bit more complicated because we have groups, we have a linear covariate, and then we also can't have a binary variable, or we can't necessarily talk the same about a binary variable as we do a continuous one. So we'll probably get, I'll do the theory of generalized linear models on Monday. And my suggestion, so Noah asked, statistically representing their opinion of how long is acceptable wait at a pub is dependent on which pub you're in. Yeah. So there's some hidden code that I'm executing that gives us a long wait output. And, what I'm going to analyze for the rest of this workbook is whether or not the wait is actually too long. So your friend waits a certain amount of time and then decides that the wait is too long. And what I'm suggesting is that threshold is different in different pubs. So you'll see as we go through this how that happens and how to predict about it. Okay? But it's all related to this concept that we've been talking about here, that all of these regression models are just ways to form expectations or predictions. And in particular, they're just ways to form conditional expectations, meaning if I'm in a given pub, I can make a guess about the wait time. And that when that pub changes, my expected wait time changes. What the generalized linear models in the rest of this workbook, and which we'll introduce conceptually on Monday, will do is allow you to have a different y, one that isn't continuous. We'll start off with y that's binary. Is it or is it not going to be a long wait? And there's a subjective factor to that, which is, something about the environment in which you're waiting. And there's an objective factor to that. Actually, how long in minutes are you waiting? Okay? So all regression is about ways to construct these guesses. And all we're doing when we fit a regression is fitting a conditional expectation. We're just saying, given that we're in this group, we have this prediction. Or given that, I'm a white 29-year-old lecturer living in Bristol, my income is this. So all of those different kind of conditional information, we use that to construct a guess. And you've seen it all the time about sort of fitting lines and all this kind of complicated stuff. And what I'd like to do from the data science perspective is just say, okay, yeah, there's a lot that we can do with fitting lines. But as we showed you the other time, a k nearest neighbor algorithm is also a way to construct an expectation. So we'll use regression because you're familiar with regression. But the main point from a data science perspective is that all regression is about a conditional expectation. It's about the prediction. What we're doing is we're modeling the predicted value of y. Okay? So it's conditional on the information I have. Given that I'm in this pub, my expected weight is this. And then here, we'll learn how to make those models for outcomes that are not continuous. And up until now, unless you're in the QSTEP program, you haven't fit models that allow you to predict these binary outcomes. So we'll talk a little bit about what's called the linear probability model, maybe on Friday, maybe on Thursday of next week. We'll talk about the actual conceptual introduction to this regression as a distributional model on Monday. Oh yeah, and we'll also do the answer key for the assignment tomorrow. So that's why, we don't really have enough time to get into the rest of this per se. And I'd like to keep the Thursdays and Fridays more code oriented and the Mondays more conceptual. But as you can see, in the rest of the notebook, well, tomorrow is practically recorded. Hannah, yeah, it'll be recorded. As you can see in the rest of the notebook, we're not really going to be fitting very much more complicated code. So it'll all just be LM and GLM from here on out. Once you know how to do these summarizes and group bys, you're fine. So where do we access the recordings? Matthew asks. So for some reason, let me stop screen sharing. For some reason, I can't figure out how to get Blackboard to accept that my my recordings for this course are linked to the course on the media site. So what I'm recommending that students do is check out the course recordings on YouTube, and that should be public. I'm labeling them based on what week they're in. Yeah, so this will be posted shortly after. So again, the main point today and the main point of this workbook is that regression is about conditional expectation. This chunk shows you that conditional expectations, predictions about whether things take on a specific value given the information that we have, those can be constructed for things that are binary, that are integer, like counts of things. They can be constructed for categorical variables. It doesn't really matter. We can still use regression on those no matter what. So we'll teach you a little bit on how to use regression on things that are binary based on their conditional expectation. So that's all I really wanted to cover for the talk part of this. And then tomorrow we'll do the answers and answers for chunk 0. And then yeah, we'll proceed on apace from there. The main lecture will be Monday, and that's where I'll really kind of get the whiteboard out and get into the nitty-gritty of generalized linear models and things like that. But I just wanted to show you these kinds of conditional expectations, means, and how they relate to one another, because that's important for the workbook. Does anybody else have any other questions on the content for this upcoming block, or how we'll get there? So for the rest of this lab, my recommendation is if you've finished the assignment due today, move on immediately to the workbook. And if you're not done with the assignment today, such as if you want to learn how to get the stuff knitted to a PDF, follow me to a breakout room and I'll help you there. Or Tom and Lenka will also be around. Okay, so my recommendation is if you're done, work on the workbook. If you're not, try and get done in this time, and then we'll move on. Oh, and before I forget, I got a lot of email about the challenge question. I know it's hard to hear, but it's a challenge question for a reason. I don't want you to spend all of your waking hours on a challenge question. If it's not something that you see how to do, it's okay to just not do it. You can still get a first. And likewise, if you do the challenge question and it takes you 60 hours, I can't accurately reward that amount of effort. You still also might get less than a first if you attempt the challenge problem. So it's just there as a bit of a stretch for students that are, do indeed have clear mastery. And if you don't, if it's really challenging to you, it's okay not to do it. Like really okay. You can still get an excellent grade in this course and not do any of the challenge problems. There aren't very many. So I would hate to think that there are students that are sort of struggling with these for an excessive amount of time. My strong encouragement is do not spend super long amounts of time on those challenge questions. If it doesn't come in a way that you think you can get it done easily or quickly, it's okay to just leave it behind. And also remember that the course is graded on a best 3 out of 4 basis. So I've put in a lot here to try and help you. So don't beat yourself up about challenge questions if they're not coming. I really don't want to hear people, neglecting other courses just to get a challenge question in this course. So please, I don't want that to happen. So I understand that, it's very fun to solve these puzzles. Maybe not so fun for some people, but just I encourage you to take it in stride. You can still get a first without the challenge questions, and you can still not get a first with the challenge. Noah says that it's hard to turn down the challenge. I know, but just because it's there doesn't mean it needs to be conquered. So I just suggest to everybody that if you're finding it's taking too long to do a challenge question, just drop it. And I won't think any less of you, and nor will your marks.